Bem-vindos to one more episode of the Type Theory for All podcast. As always, this is your host, Pedro Abreu, and in today's episode, we will talk with Guannan Wei, my colleague from here at Purdue University. Guannan has finished his PhD last year under Tiark Rompf and is currently doing his postdoc with Tiark. Guannan has worked on a plethora of different compiler stuff. And in his conversation, we will talk about staging, Futamura projection, symbolic execution, compiler application, smart contracts, and quantum programming. Towards the end of this episode, we also talk about his application experience for the position of a professor here in the US and a few other countries. Now, before we get into this episode, I'm very excited to announce that I'll be working on this podcast full-time next semester. That's right. I have so many good plans. I'll finally be working on the YouTube, developing shorts, cuts, have more presence in social media such as Instagram and TikTok. And in order to make this possible, I am counting on finding partners in industry. So if you work in industry and you think that your company would be interested to partner with us, please contact me directly. You have my email, typetheoryforall@gmail.com. And of course, if you're not in industry and your help will also be highly appreciated, go to our website and donate through our Ko-Fi platform. Any amount will be of great help. Don't forget to join our Discord. Being part of the community, Ko-Fi subscribers also gain exclusive access to Discord channels, and we are able to send exclusive questions to our future guests and even participate in our recordings. Go to our website today, typetheoryforall.com, and become a subscriber. Now, finally, without further ado, let's get into this episode. Today, we have someone from the same university as I am here at Purdue University. You know, I wish I would have the chance to talk with more people here. That is definitely the plans before I leave. So we are starting today with, we're going to have a great conversation with Guannan Wei. How are you doing today, Guannan?
I'm doing great, Pedro. How are you doing?
I'm pretty good. The winter here is surprisingly mild this semester. I'm very happy. Today is a beautiful sunny day.
Yeah, the weather is really great today. Yeah.
So, Guannan, I was looking into your CV and your statement. You're going through the whole application process of becoming a professor. You're only applying here in the US?
I also applied a few places in Canada and Singapore and China as well, but very few places, mostly in the US. Yeah.
We're gonna be getting more into that part in a little bit, but before we get there, I would like to ask you, because I saw that you started your undergrad as a law student. How was your path towards becoming a computer scientist and becoming a PhD in programming languages?
Yeah, that's a long story. I think in high school in China, I was, before the master's study, I was all in China. And in high school in China, there are two tracks. One is for science and one is for liberal arts. So in high school, students take different classes and they take different exams for those college exams, right? So in high school, I choose this liberal arts track. So I study history, I study politics, geography, and so on. I didn't put a lot of efforts to study physics, chemistry, those on. So that's kind of, so when you choose a college major, you can only choose those liberal arts majors in college. So when I get those college entrance exam in China, that's, I think, almost 15 or 14 years ago. So I only have a limited set of majors I can choose. Then I just somehow ended up into law major students.
So what are the majors you can choose in liberal arts?
Literatures, I think business management, law, different kind of languages.
And then after a couple of years, then you choose the specifics field.
No, it's kind of complicated for my undergrads because I studied laws in the first 2 years, and then I tried to transfer something more close to tech, to computer science, but I can't really transfer to computer science in my college because there are more courses I need to take to make it happen. So I ended up transferred to business management, or it's called management information system major for the rest of my college, and also has to take additional courses. So my whole undergrad study takes like 5 years to finish because I need to take additional classes. This management information system is mostly still a business major. You study accounting, you study HR, you study Oracle databases, SQL, a little bit business analytics, those now part of the data science stuff. But I think the part is during that time, I get into somehow Scheme, the Scheme functional programming language.
For sure.
I somehow learned those things from the people talking about those online. And I get into this book, The Little Schemer, by Dan Friedman and Matthias Flessen. That's kind of the really point that I get into functional programming, and also take chance to take a few Coursera classes. Coursera is online learning website. Yeah, I think at the time there's a Scala course on that, and there's also a PL class from Dan Grossman, I think.
Oh yeah.
Yeah, on this Coursera. That was I would take in my spare time during my undergrads. That's kind of the experience how I get into this program languages, and eventually decided to study computer science later.
So you actually started with when you started programming, it was directly with functional programming then?
No, I know a little bit programming since childhood. I played with those VB, Visual Basics. You can draw those buttons, forms, GUI stuff, and Delphi, and a little bit PHP as well. Right, those are kind of the easy piece. You can really get started by just looking at some tutorials, right?
Mm-hmm.
But I think I didn't really understand the real stuff about programming until I learned Scheme. Yeah,
I see. It's very interesting. It seems to be a very major shift because you're studying law and then some business. It's very different from the world of things that we do here in programming languages. And then you're doing these things on your spare time, and all of a sudden, what was the next step? You're like, okay, I'm going to do a master's in this. This is what I want. How'd that go?
Yeah. I mean, I did a lot of stuff in my spare time, which also means I didn't do very well for my undergrad major.
Priorities.
Yeah. I got a pretty low GPA for my undergrads. That's really hurts, grads application as well.
Really?
Yeah. But I mean, I still submit a bunch of master applications, and I just look for some of the universities or departments they have people working in program languages. So I think eventually that was 2015. I ended up with University of Utah. Where at the time, well, there are a lot of people working in PL and verification compiler at Utah. There's still more people there. Yeah.
All right. So you ended up in Utah, and what were you working on over there?
So at Utah, I work in the Marmite lab. Marmite was there as a associate professor, I think, at the time. So he has a big lab working program analysis mostly, and several, I think, DARPA projects or something about like applying program analysis to address problems in cybersecurity or those checking vulnerabilities in Java programs. So I started working in the lab as a RA, research assistant. It's mostly kind of the specific project I'm working on. It's kind of building an abstract interpreter for Java spy code. It's kind of like those static analyzer stuff to see if there are some inputs to a Java program that can trigger, say, consuming large amount of time to finish a run, or assuming a large amount of memory resources for the program. That's kind of considered as a algorithmic attack. And we're working on analyzers to detect those vulnerabilities.
Mm-hmm. So more software engineering kind of thing instead of more compilers at that point.
Yeah, I mean, as a master student work on the project, I think mostly I'm working on the engineering aspects more, like implementing those stuff in Scala. And yeah, also, I mean, as a master student, I also need to take classes. I think I took 10 classes
10
for the two
classes? Wow.
for the
Yeah,
two
that
years. Yeah, for
sounds
master student,
reasonable.
that's kind of a norm.
Yeah.
Yeah.
So that was did you also have to do a thesis option? Because I think at Purdue it's 10 classes without the thesis and 8 classes with thesis, something along those lines.
I wanted to do that, but I think eventually at the last semester, I realized I underestimated the effort of
For a
doing a
thesis.
thesis.
Yeah, yeah.
And at the time, I don't really have a publication. I just have a project to work on, but turning it into a thesis and getting scheduled for defense or so on. I just didn't, at the last semester, I didn't allocate enough time for that. But the lucky thing is I also take 10 classes, so I can just say I'm going to graduate
Yeah.
as a course-based
Yeah.
master
For
student.
sure.
Yeah, yeah.
So then you finished that, you applied for a bunch of PhD, did a bunch of PhD applications and ended up at Purdue.
Yeah. I think at that time, my master advisor, Matt Might, he decided to go to somewhere else. He because he kind of transitioned to those precision medicine area. If you know his story there. So I think all the students in our lab all applied somewhere else. So I also applied a bunch of places, and then later got here at Purdue. I think we met at the USLA summer school before
OPOSS summer school?
Yeah, Oregon
Yeah,
summer school.
I was actually looking at your CV and I'm like, I think we met there, but I don't remember.
Yeah, it's also a vague memory for me as well. I think that's a 2017 or 16. I can't remember because
it was
I went to there
17.
twice.
Yeah.
Okay, 17.
I think I was there for 17, yeah.
Yeah, at the time I just graduated, and that's the summer between my master and starting at Purdue. Yeah.
I had such a great time over there. That was
Definitely
what made me choose. Yeah, this is what I want. I want to do a PhD in this field in the US. Seems amazing. It was so good. The professors, the classes there were great.
Yeah, this year it's going to be at Boston.
Oh yeah, what is it? Is it in May, June, May, right?
Yeah, sometime in summer.
June,
I don't remember what exactly there.
Yeah, one of those 3 months. Oh, that's funny. Oregon Programming Languages Summer School
at Boston.
At Boston.
Yeah.
But hey, at least it's happening.
Right.
So when you got to Purdue, did you already know that you wanted to work with Tiark specifically?
I think I got some ideas that I could work with Tiark, especially. I think staging is cool, which is kind of the most visible topic Tiark did at the time, I think, or at least the things I could understand at the time. Yeah, I think that's a cool thing, and I have some rough idea about applying staging to program analysis. Later becomes my part of my dissertation topic. But I think one of the reasons at the time I chose Purdue is there are many other different professors working on a lot of diverse things. So I think that would be a good environment for me to, I mean, even at the point I'm not sure about which specific topic I want to work on, but there's enough diverse and vibrant environment for me to explore.
Yeah. And you are definitely one of the. I think you're the most senior Tiark student here by now, right? Everyone, a lot of students
I'm already
left.
A postdoc.
A lot of people went to industry. Yeah, there are so many great opportunities in industry in our field right now that I think a friend of mine was telling me an offer for internship at Amazon that he received this summer. I was blown away. That is like twice the amount of money that I was offered when I was at Galois, for example. I was like, whoa.
Yeah. that explains why
people are leaving and why people are leaving for other companies, and there is AWS happening over there. Yeah, it's it's a thing. It's definitely a
Yeah,
thing.
yeah.
Which
It's just
actually
really well paid. Yeah.
which actually surprises me a little bit. What were your considerations to remain in academia? Actually,
I just felt like academia, I have a bit more freedom to work on things that I get interested in instead of following the company's agenda. I mean, which is not necessarily a bad thing, but for me, I felt like having this space and freedom to explore things following my own interest would be a bit more important. I think another thing is in my undergrads, I also did several times of intern in China and both a few times intern in US. I got a feeling about what the industry looks like, especially sometimes because you're mostly, I guess most of the time you're doing like a software engineering task, developing stuff, working on those things can be really applied to actual problems and making production and revenues for the company, which is good. But for me, I felt like the salary or the money stuff from the being an academic profession is good enough for me. So yeah, but it's even lower. I would seriously reconsider that.
no, but we talk like that. It's not as if professor salary is bad either. Especially here in the US, the salaries are pretty good. They're very
Yeah, yeah, yeah,
competitive, really.
yeah. That's totally enough for me.
But at the same time, I feel like I definitely agree with you. I've also done a couple of internships in the industry. And one feeling that I always have is towards the end of the internship or after a couple of months, I start feeling a little bit bored in the sense of sometimes you start seeing the same problems pop up again. You're not necessarily working with something that is novel. You're more worried to use technology that is already there and make sure things work and is robust and maintainable. And
Exactly.
sometimes this maintainability, you will be doing the same thing a couple of like over and over the years. Sometimes it's
Yeah,
nice to
exactly. Hmm.
it's really nice if you're interested, like it's a lot more stable, and you have a more peace of mind. Usually you have your weekends for yourself, which which sometimes in academia you're not gonna have that luxury.
Yeah. Well, sometimes you have more choices in academia, right?
There's that too. Yeah,
Yeah,
yeah.
yeah, yeah. You can
There are more
say
freedom. Yeah,
for this month, I'm just going to take off and I don't really care about those things. I want to take a rest. That's possible, right? Or at least at least I felt like you will have more flexibility there.
yeah, yeah.
Yeah, yeah. But yeah, but there's no really like absolute freedom there, right? In
For
academia, you
sure.
have constraint from teaching, and especially, I guess, in US, most of those research universities, faculties need to get grants proposals. That's also kind of a major labor work for professors. Sometimes people are getting not really hands-on or has time or energy to work on things in a very close way to actual project, which is which I know some people, they leave academia to like companies like Galois or more researchers companies because you have more time to solve the actual problem instead of dealing with proposals or administration, teaching. Yeah.
I definitely feel that often enough. I don't know about Europe, but here in the US, professors have a more management role to manage the students and make sure everything's along the lines and writing the grants and polishing the publications and giving classes. And probably they have so many annoying meetings as well. Like those meetings of the department to figure
Service.
out.
Yeah. 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 Service.
Uh,
Yeah.
how's it
Serving in
called?
different committees. Service. Right.
Service.
Yeah.
Yes. Oh
Yeah.
my god.
Yeah.
I think I
Serving in
would hate
different
service.
committees, undergrads curriculum, or different committees at different level, department level, college level. But for assistant professors, you really don't have to do a lot of those things, because I think usually a department knows that you need to focus on research. So they will not really assign a lot of committee work for you.
Oh, I see. Gotcha. Yeah, that sounds good. That sounds pretty good. But let's talk a little bit more about your research. You were saying, let's start where you were saying that when you came to visit Tiark, he was working on
staging, multi-stage programming.
What is that?
So it's basically a programming style allows you to write programs to generate other programs. That's a very high level description. And the benefit of doing so is that you can generate programs that runs much faster. Or saying you can optimize the generated program by specialization. You seem to be confused.
Just a little bit. A little bit. Compiler is not necessarily my direct field. I just have, like indirect experience with compilers. But so a staging mechanism, let's see if I got this right. It's kind of this framework infrastructure that you will write a high level specification of how your program is supposed to work, and then it will kind of deriving things for you. Is that kind of the idea?
Yeah, roughly like that. But I can give you a little bit more concrete example here. So think about you're writing a power function to compute, say, the number of b to n, right? And you have two inputs for this function. And you have a base number, you have an exponential number. And you can write this program to say, I'm going to write this function's power function recursively, and I can say whether the n number, the exponential number, is 0, then I just return 1. Otherwise, I will return a value that is b times a recursive call that decreasing the exponential number, right? That's kind of like a pretty straightforward functional way to write this power function, right?
Yeah.
But sometimes you will often find that those inputs b and n, this is a general function, right? But sometimes you want a more specialized function where the number of n. You just want to compute, say, b to the power of 3, right? A more straightforward way or more efficient way to write this down function is just b times b times b.
Right.
That's what we say it's more specialized version. And multi-stage programming, or generally partial evaluation, is a mechanism to derive this more specialized program from a more general program. And that is done by, say, what is n at the first stage, right? It's called multi-stage. It means that those different arguments at different stages. The number of n in the first stage, and you want to ask the system or library or the underlying program system to say, okay, I know this number n here. Give me a more efficient and specialized version of this function. That is already computed all the computation over n here. And this is generate another program for you.
This example in particular is very similar to inlining.
Yes, it's kind of like inlining, but it's also unrolling the recursive calls, which is something usually the compiler would not do for you. Yeah, this is a more like a programmer controlled way to do inlining.
Interesting.
So this multi-stage programming starts from 90s, but there are more prehistory to that. I think the research starts from early 70s, and people realized this thing called partial evaluation.
Oh yeah.
And I think at the time, one of the most intellectually interesting stuff is how to derive compilers or how to generate compilers automatically. Because at the time, people studied semantics and thought it would be nice if we can generate compilers directly from the semantics, right? Instead of building a compiler, say, using an RVM framework, writing those passes or code generation passes, right? And the dream is to say, we have somehow a semantic description and we want to automatically generate compiler. And that goes into this idea of Futamura projections, right? Where you have an interpreter, right? You can think of interpreter is somehow similar to the power function I just mentioned. And this interpreter, simplified speaking, you have two arguments. One is a program, or say the representation of the program. That is, can be the AST, abstract syntax tree of the program, and also the input to this program, to this object program. And then you can say, I know the program to be compiled, but I don't know the input to that program, right? And then you can specialize the interpreter with respect to this AST of the program. Then you generate another program, can still taking the dynamic input to that program. That is essentially of compilation. So that's a first level of Futamura projection. And you can also really do fancy stuff to have higher levels of those Futamura projections. For example, you can specialize the specializer to an interpreter that generates a compiler program for you. That's the second Futamura projection. You can even go one level up to say, I'm going to specialize the specializer with respect to the specializer. It's really mind-blowing for the first time I saw it. Because that gives you a compiler generator, which is this compiler generator takes an interpreter as input and gives you back a compiler.
Wow. And is it like, what are the drawbacks? That sounds like really, really, really good.
Drawback, it's not directly straightforward to see how it works for those modern hardware and modern architectures, right? Because this is all about, or straightforward to implement this thing is all about self-application. You're basically, because you need the capability to manipulate the program, right? And that's all in the same language as your meta program. That's at least traditionally how it's done. And say people have been built this Futamura projection stuff or compiler generator in Scheme, because Scheme is a language that you have those homogeneous representation of both code and data. That's very easy to implement those things. But if you really want a high performance implementation generating like assembly code, somehow you have more work to do. I think, but this is still a really idea that shows a deep connection between interpreters and compilers. And it's also a very beautiful idea to kind of twist your mind to see how you can play around those things, which is really fancy. Yeah.
And when you have this compiler generator, are they gonna generate compilers that are fast enough to be compatible with the state of the art? For example, C, for example, you generate a very complex C compiler with that. Is it going to be a good compiler? Is it going to be a regular compiler? How does it compare?
I think nowadays people mostly give up to build compiler in this way. It's just has too many problems. It doesn't really talk about how you can represent the runtime data structures, right? It doesn't talk about how you generate lower level code, right? There are more compiler passes if you really want to have a generating very high performance code. So I think one of the practical use here is really the first Futamura projection, where you have an interpreter and you can derive, or you can essentially taking the process of specialization as compilation. This is also close to some of the industrial virtual machine, how it works, like Grail VM from Oracle. That's essentially like a pretty close to the first level of Futamura projection.
In what sense does the LLVM is a Futamura projection? I cannot see that.
Well, I'm not saying LLVM is a Futamura projection. I'm saying the Grail VM, right, from Oracle.
Oh, okay.
It's kind of like you write an interpreter, and the framework underlying will take this interpreter to give an input to specialized interpreter to generate code, which removes the overhead from the interpreter as well. Because you can think about the interpreter as a description about the semantics.
Right.
You can take it either as operational semantics or denotational semantics. It's just to write down kind of like an equation to say, for this specific AST, I'm going to do this.
Right.
right? But what it does really, you can also reify what it does to its code,
Mm-hmm.
which essentially become compilation.
Ah, interesting.
Yeah, I felt like maybe it's sometimes hard to talking about those things to see how it works.
Yeah, that's one of the challenges of this media of having podcasts,
Yeah,
which is also makes things a
yeah,
little more fun too, because it makes us to be a little more creative to
yeah,
show those ideas without using pen and paper or slides or any of that.
right.
So it's different. It's fun.
Yeah, yeah.
Do you know what the name come from? Futamura, is that the name of the first author?
That's a Japanese computer scientist.
Okay.
I think
And why is it a
for,
projection?
it's kind of for projecting programs from the interpreter, I guess.
Okay.
If you think
Interesting.
about projection in the sense of extracting something. I think the original work from Futamura was published in 1971.
Oh,
That's
that's
pretty
pretty
old.
old. Yeah.
Yeah, yeah. At the time, I think there was no ML, right? The meta language,
I'm not
right?
sure, but yeah, it feels like it should be around 75 or something like that, 76.
Yeah, and six partial evaluation, I think, was pretty active research area, at least in the 90s.
So what are you guys doing with it nowadays?
I think this idea is still interesting, right? It's a fundamental idea to tell you something about the semantic artifacts about interpreters, about compilers, or about different ways to build tools for languages, right? It connects those different tools. And for me specifically, I was trying to apply this idea to static analyzers to derive compilers for static analyzers. In this sense, if you think about people build abstract interpreters or program analyzers, mostly by writing down an interpreter, right? It's not a standard interpreter, but roughly if you like the program structure, it follows the same idea, right? You have a giant switch table or pattern matching to see for this assign node, I'm going to say I have a store structure. I'm adding a new value into the store, right? For a while loop, for example, for an abstract interpreter, I'm going to compute a fixed point here to iterate over the lattice structure, right? That's still like interpreter. But a better way or a more performant way, if we look at how those things are done in the concrete space, people are building compilers to generate code to perform those computations, right? But for abstract interpreter, the idea I have is we can also do the same thing, and we can really scale this approach to very far, and applying this idea to different style of analysis. That's kind of essentially like applying the first level of time projection to static analyzers, to abstract interpreters, or to symbolic interpreters, or different ways to analyze the program, but as a compiler.
So what kinds of static analysis tools could you work with to apply these ideas?
One of the I applied this to both sort of this abstract interpretation for higher order functional programs, which is basically doing control flow analysis. And this is kind of computing what are the possible lambdas is possible for a call site, right? Because this kind of control flow analysis becomes undecidable for functional or higher order programs. And this can be addressed by a form of abstract interpretation. And this is one thing I applied to. Another thing is applied to more lower level LVM-IR for symbolic fusion. This is more close to practical test case generation. So in this case, you have, say, in a C program, you have an assertion statement, but you want to see or generate test cases to see whether there are possible inputs to trigger this assertion to make it false. That becomes a runtime error, right? So symbolic fusion is a way to find bugs for those things. And that's also traditionally is constructed. Most of the time it's constructed as an interpreter. And my work is mostly building a compiler for those analysis.
Mm-hmm. Very interesting. And you also done some work with reachability types.
Yeah.
Can you tell more about it? Is it related to these ideas of the symbolic executors or analyzers, or is it completely different stuff?
Well, it can be related, but I think so far the development looks very different. So this reachability types, it's kind of starting the idea about how can we introduce those ownership types or tracking side effects more precisely in functional languages, and at the same time also allowing to use functional program idioms or first-class functions in a more flexible way. Um, part of the thing is motivated by Rust. If you think about Rust, it has this ownership types, tracking lifetime, right? Those are very good to control how those low-level resources are used, but it does not directly apply to functional programs. Where if you think about functional programs, you have first-class function, right? Those first-class functions, they will become closure values at runtime, meaning that those functions, they become a pair of code and also data. And those data, they are captured from their defining scope, following the lexical scope principle, right? And if you define multiple functions in the same scope, right, they will naturally capture the resource or variables defined in the same scope. That's kind of like a sharing thing from induced by the first class functions. But this is not directly compatible with Rust. Like Rust has this restriction called shared XOR mutable, and but it's kind of a very restricted way to say how resources can be shared and how it can be mutated. And also in functional programming, you have those functions can escape, right? You can return a function, and this return function can capture something defined in the local scope. And once you escape, how do you know, or for the programmer, how does the language or type system track how those resources are used or shared? That's kind of the way that we want to use or developing the reachability types to address.
So the idea is to have some sort of tracking of what is reachable from where. That's the idea of the name.
Exactly, yeah. But this is also has to work with functions. So you can think about the type system has additional what we call as a qualifier. It's basically additional components in your typing judgment, right? Those are set of variables, and those set of variables, they track what can be reached from the evaluation result of this term in the context, in the typing context. That's roughly that. But this is, of course, now the first. We're now the first one to apply this idea. There are, like, if you think about some form of region type systems, they have also similar ideas before.
Yeah, this sounds very very new things. Even though you're not the first one, but I'm always amazed by the kind of research, by the kind of things that Rust is implementing. I think this is absolutely mind blowing, and the kind of very new effort into compilers that they're putting is very very interesting.
Definitely, yeah.
Is there any other new compilers thing that you think it's worth mentioning that you've seen been used or been developed recently?
New compiler things. I think from academia there are a lot of different prototype-ish language. I'm trying to think of. I think there's a Pani language. Do you know this Pani language? I think from the from where I'm trying to see it, from somewhere UK. I think but it's kind of like tracking capabilities and also some similar idea of ownership types for high performance computing, if I remember correctly. And also for industry, there are, this Mojo language kind of getting a lot of attention last year.
I don't know about that. I've been so out of the loop. What is Mojo?
James Decker works there.
Who? James? Oh, James. Okay, yeah, he used to be from your lab. Yeah.
Yeah. So they're trying to build Python-like AI language, but providing more performance and also
I've seen that language. Now I remember. Yes.
modular AI.
Right.
Yeah. And the interesting thing is they're also trying to add, I'm not sure the latest status, but last time I checked it, they're trying to add some style of ownership types and lifetime tracking in the language as well.
What do you need for a language to be good for AI? Do you have any ideas about that? Have you?
I honestly think it can't be too complicated.
It's just AI. That's a good answer.
But I could think about some of the cases it can be useful, right?
Mm-hmm.
You want to see how those resources are allocated and used, especially you have a large chunk of memory or matrix or data.
Yeah,
right? Yeah.
Highly parallelizable things.
Yeah. If you know those things are stored on different storage and they do not interact with each other, you can easily parallelize those things.
Yeah. I think I have a friend that he's working on some matrix multiplication sort of thing, which is very important for AI work, and it gets highly non-trivial very fast, which is very interesting because, we've been dealing and optimizing this kind of things for a long time now and still have a hard problem. It's very surprising for me.
Yeah.
But you've also been working on a prototypal language, Diamond, I think.
Yeah, that's what kind of we implement the reachability types as a prototype.
Oh, okay.
It's just kind of implementing the type checker and also a little bit inference. We're still working on the inference part. Yeah, that's but it's still a tiny prototype language.
What does it have?
Got more it has basic function definitions, basic data types, and the
functional
type checking. Yeah, functional. It's functional language.
First order functions.
You have higher order functions.
Higher order functions.
You also have the basic memory allocation in a style like malloc, right?
Really interesting.
That's how the reachability types works. In a language, it's both functional and also imperative.
Like Scala-ish.
Scala or OCaml. Right.
I think Scala is such a funny language, man. Scala is like you do whatever you want, however you want. Just go for it. You want imperative, go for it. You want functional, you got it. You want maps, folds.
Mix all notions there. Yeah.
It can become a mess real fast, but it's really fun to program in Scala.
Yeah, I felt like sometimes OCaml in a similar situation, right? You also have object-oriented programming stuff there, mutable references.
Yeah, but you don't really use mutability.
Yeah, you don't really use all stuff. You also have those modules, right? Functors and module.
Right.
OCaml. Yeah. That's more common.
Module? What is that? Modules. Modules. Yeah.
Modules and functors.
Mm-hmm. Yeah.
Yeah. And people do this crazy PPX stuff for OCaml as well.
Yeah. I think does Scala have type classes?
Yeah, you can do type classes.
Oh shit! Easy. So you have the full monadic interpreter.
yeah. That's how I build my interpreters for applying Futamura projections.
Oh,
you can do
damn.
monadic interpreters as well. I mean, you can pretty much translate any Haskell code in Scala in a very functional way, or just kind of what is called point-free.
Yeah,
you don't even need to mention explicit variable names.
Which is one of my beefs with OCaml. I love OCaml. I think it's my favorite language nowadays, but you cannot do really point-free program. Like the programs compared to Haskell is a lot more ugly. It's good because it forces you to program in a very particular way, and your programs are much more straightforward. There's nothing crazy happening at any point, which is great for productivity. But Haskell it's so much more clean, and you do it's intellectually stimulating using Haskell.
Yeah. The trouble I have is every time I look at the code in OCaml in Haskell, it's point-free. I need to staring at one line of code for a
Yeah.
long while to really understand what it's doing. It's just a single line, right? It's compositional functions, applying those applicative functors.
And then you have those dollars and stars, something.
Yeah, for some point for readability, it's really bad. I think, especially for people who didn't write this code or who write this code a long while ago and trying to remember what it does.
But feels really good coming up with this one-liner and this idea that you wouldn't be able to do in any other programming language. It's very fun. It's very fun.
Right. I mean, I did something similar in Scala, or at least try to do that. You can because in Scala you can also have define infix operators pretty easily.
Really?
That allows you to do those compositional kind of phrasings. Yeah.
I'm telling you, Scala, you can do everything. Scala is like the ultimate programming language nowadays. I want to see a language. Like the only thing that there is only one language that I know of this, which is the use of notations, which is Coq. Right? Coq allows you to change the AST of your program in runtime, which I think it's the absolute most mind-blowing feature a language can have.
That's meta-programming.
Exactly.
Right? Exactly. Yeah.
But
I think Lean, you can also do this pretty easily.
Yeah.
Lean.
Okay.
Yeah. You have those notation, or it's basically kind of defining some sort of parser in your language.
Exactly. You're modifying the parser of its own language in runtime, and it's so broken. It's so broken. Why would you do this?
Yes, sometimes I don't know. It's this level stuff in Coq always sometimes get me confused. What's the right level I should define, and how this compose with other things?
Yeah, I get it though. Because we are doing mathematics, and we have to come up with our own language and make things a little more pretty. But in a purely programmatically perspective, it's such a bad idea because every single time I open a new project, I basically have to learn a new Coq language, basically.
Yeah.
Right?
Yeah, you always see different symbols in Coq projects.
And then you have all this preparation that you have to go through every single time. It's insane.
And sometimes new ways to type those different symbols in Coq for Emacs.
Right. There's still the Emacs stuff. Yeah.
And similar for Agda as well, right? Agda has way more Unicode symbols as well.
Yeah. I don't know what is my opinion about Unicode in programming. I think that overall it's fun. It's a good thing, I think it depends a lot on the kind of IDE you use, because if you're using Emacs and Agda, it goes hand in hand. It's great. But with VS Code, for example, I'm not sure how easy it is to make things.
It should be pretty easy. I use a Lean plugin in VS Code. It's pretty smooth. You can type all those letters. It has a built-in input method similar to Emacs. Pretty convenient.
Nice. Yeah. It's exciting.
I think the trouble is if you have multiple people working on those things, you have to have the kind of agreement what's a programming style. Otherwise, the other people may get trouble to type those things or to catch up on those code.
But in one way or another, that's kind of like always an issue to come up with some, what's the word? Making sure that everyone is more or less using the same style of programming so that things doesn't go too crazy. It's a good thing. But that's why again I like OCaml. It's because honestly there's not much ways to do one thing. There's one way to do one thing. That's usually a good thing. But
that's kind of basic. People don't use object-oriented programming in OCaml. Right?
Yeah, there's that too.
There are more ways, but people just have the consensus what
exactly, and the mutability and that sort of stuff. But anyway, so we talked about Futamura projections, we talked about Diamond, we talked about reachability types. Is there any other compiler research that you think it's worth mentioning at this point that you've done?
Compiler research, I think maybe another interesting step is for this reachability types applied to compiler optimizations.
Okay.
Where we had the kind of design a compiler IR. It's typed IR, so you have type information attached to the IR. It also tracks the reachability of different resources and also side effects. And overall, that's IR, compiler IR, intermediate representation is a graph, and the nodes are terms or expressions. And also you have edges are dependencies, data dependencies or effective dependencies. And that's the whole program is represented by a graph. And that allows you to do a lot of optimizations, for example, about code motion. Some of code doesn't have to be scheduled there, or it can be lifted to a higher level to enable more sharing. Or you can do optimizations for imperative programs where you have, for example, 2 consecutive write or write into a single memory location. And if the first write is not used anymore by any downstream computation, it's safe to remove those things. That's kind of the way, a more smooth way to optimize imperative programs as well. So this is essentially the idea that the internal representation of the LMS framework, Tiark and our group build.
Yeah, I can see that. I can see how useful that is. Like it's giving more information to the compiler that you can work with and you can use towards transformation and optimization and all those good things.
Right, especially in general, this is in a higher order and imperative setting. Your program is natively higher order, and you also have side effects, which is the difficult scenario for compiler optimizations. If you have just pure program like Haskell, everything is pure. You don't really have side effects. That's easy. And if you don't have higher order functions, just like LVM or C, you still have pointers to deal with, but most of the time your functions are first order, and you don't need to take care of those tricky case like escaping or functions as argument. That's also a bit easier to optimize, like LVM does. But those combination becomes an issue or an open research direction there.
I see. Interesting. I never thought about that. Yeah, it makes a lot of sense. It does. Yeah, higher order really is really a blow, especially in the context of, like function that has some context and variables can escape and those ideas. Yeah, pretty cool. At some point, you mentioned that you've been using some ideas of algebraic effect handlers to do some stuff.
Yeah. The specific thing, algebraic effects is kind of a fancy way to do monadic programming, right? You have those more compositional way to write down the program has side effects, and you disentangle from the program and the interpretation of those side effects, where you have handlers, right? And the people have been exploring a lot about monads and how it can be used to construct an effective program, right? Monads, monad transformers, and which are kind of good to some degree, but like monad transformers, you have to layer those monad transform, which can be cumbersome to use. And algebraic effects is a nicer way to write those effective program. And the way I use that is to write down, or as a way to write down language interpreters, where you can think of a language interpreter, right? I'm interpreting a effective language, right? This language has side effects, then I can use a state monad or state effects to model that. So interpreter itself is stateful or effective. Then I can write down a generic interpreter that issues those side effects. Then later point, I can apply different handlers to interpret those side effects induced by the interpreter. And if you think about program analysis, you can also write down the program analysis interpreter in this style. And once you apply different handlers, you can say those handlers are different strategies or different ways to actually perform the analysis. For example, in program analysis, sometimes you need to explore 2 branches. Once you have this condition that is not statically known to be true or false, then you need to explore both branches. And then you can have some more different strategies to how to perform those non-deterministic exploration. That gives you a bit more flexibility and disentangle the actual analysis strategy from the semantic description of the analysis, which is you can think of a specific use of algebraic effects and handlers.
Gives you different strategies very easily. Yeah, that's very
Makes sense.
very interesting. Yeah, makes sense. About metaprogramming and deriving compositional analysis for free.
Right. Yeah, that's something I've been thinking for a while, but I really want to actually get working on it. It's kind of the idea that you can easily write a program analyzer that works for the whole program, where you have all the source code information available, and you analyze this whole program to get some useful information or to check the property of the program, which works, but only when you have the access to the whole program. But sometimes you don't have the access of the whole program, or codes are changed all the time. Think about you're in a company, people are committing code all the time, right? And easier way or a better way to do this is to say have this compositional analysis where you can analyze each modules or each program unit separately, and you can produce a summary from this program module or unit, or say a function or a class. Then at the point you have all those summaries available, you can compose those summaries to get the final analysis or analysis result. And that's a more adaptive way to deal with code changes or evolution of the software. And that's generally called separate analysis or compositional analysis. And what I want trying to do is to see to what degree we can mechanically obtain these artifacts for composition analysis, given the whole program analysis or whole program analyzer. And the way I look at it is kind of like a metaprogramming problem. And that's kind of given the whole program analyzer, can we tweak it or transform this analyzer itself to derive or to obtain analyzers that can be applied to program unit? That would be much easier, because in this way, to design a notion about what is the right summary and how to compose those summaries are for free. It's not something the static analyzer needs to take care of. It's become part of the construction that gives you.
What constitutes those summaries? What is in there?
The summaries, they are mostly partial information that is analyzed given this program unit. Like what are the analysis can be done by just looking at this partial program. But also it has some kind of binding like things to say, when I know other information from other part of the program, then how those things will affect this program module or its behavior.
Do you have an example?
That's like a summary. I think one of the simple summary is precondition and postcondition. If you think about the function, that's either example to say, right? But that's more like in a logical setting. That gives you the condition of the function, what they expect from other programs, what it guarantees by running this program or this function. Yeah.
Then have you been doing some work with smart contracts as well? I see that you've mentioned it, some parts of your statements.
Yeah, I work on that one with some friends here at Purdue as well, and we kind of get molded by some of the security issues in smart contracts.
Oh yeah,
right. There are those decentralized financial applications, but those applications get attacked and people lost real money from those projects. But for the programmer perspective, you can address those problems by making your smart contract programs more robust, right? And one of the idea we had is how about we enhance the language design to provide more facilities to allow programmers to annotate those functions with the precondition and postcondition. And that's kind of the idea about behavioral contract. If you think about this FL style behavior contract, or they're also available in Racket and other languages as well. And those behavior contract specifications, they're checked at the runtime. But I think the important thing is the language itself has to provide such linguistic mechanisms to allow programmers to attach specifications or conditions, preconditions, postconditions, to function arguments, to function return values. That's really an old idea, maybe from 80s, right? But this is something kind of unfortunately missing in those smart contract languages, like Solidity, which is the one we targeted. So we kind of designed a language extension to Solidity and to allow those things. I think the interesting bit there is that Solidity is such low-level language. It also has a notion called address in a similar way like pointers in C or address in C. And those addresses in Solidity, they can be either, say, referring to another user or referring to another smart contract. And those addresses can be passed around, and you can invoke functions onto those addresses. But those addresses are kind of opaque in some sense, just a number, right? And those addresses, when they use the argument, then in the function body, it will say, I'm going to call this function f of this address value. Then the way that we do it specifically is to also allowing those attaching specifications to address values. So when those addresses values, they are called with some functions, then we can also enforce those conditions. It's kind of similar in the way that those addresses are used as a function, as a higher order value. And we want to check those conditions at runtime. Well, to be precise, it's not entirely higher order as we did, because you can pass addresses value to addresses values. That is a point that we cannot really check. But that's getting some into details. Yeah.
So it's like developing Daphne, but for smart contracts.
Kind of, but we're not doing static verification. But it's possible to do that. But the specific work I've done is runtime verification or runtime checking, runtime validation.
Right. So basically, if something is about to break, it's about to spend too much money that you know that shouldn't be done, instead of doing that, you just break. You're just like, whoop, something went wrong. Let's just stop here.
Because those transactions of smart contracts are atomic. You break at the middle, then the whole transaction will just revert it.
Gotcha.
And in this way, you can write more complicated conditions because you're just a runtime program for those conditions, like a property you write in the same language, and that will be executed at runtime to check if this condition will hold. That's just more expressive or easier to use, I would say.
Nice. Pretty cool. Yeah, once you're describing, I was thinking of static verification. Then you would need like SMT solvers and things get much more complex all of a sudden.
Yeah, there are definitely a lot of people working on static verification for those problems. And I think Jenna, she's also looking at gradual verification in the middle of, which I would think can make more sense because not everything you want to check at runtime, which can be expensive, and not everything you can easily check statically because that becomes impossible or too imprecise sometimes. So a middle ground would be also make a lot of more sense as well.
I also built some formal models for what in Coq for C-like languages, some Uppsala work. What was this?
Oh, that's what we call closed form or collective representations for with low-level code. Yeah, that's the one I worked with Greg, who was a grad student here.
Esertel.
Yeah.
Is that him? Oh, yeah.
Right.
I think he actually built most of the compiler scores. Was him, right? Here at Purdue.
Yeah, he was involved a lot in the compiler class development here.
That was a really good course. Gregory made a really good job. I think he got two really big what's the name? Prizes when he was graduating. You got a good prize too, right? You got a good prize when you graduated. What was the name of the prize you got?
I think that's Hofstad.
Hofstad.
Yeah, I think Greg got that as well. Grad also got a teaching award.
Yeah. That's some really good stuff.
Yeah.
What is this award you got? Congratulations, by the way.
Thanks. Yeah. I mean, the award is somehow for software engineering research in journal, I think.
Oh, don't put it down, man. It's a good award. It's amazing stuff. Only you got it in your year, so there you go.
Yeah, it's kind of once a year. Yeah. It's a good award. Yeah,
you deserved it, man. You did an amazing
really
job.
happy I got it. Yeah. Of course.
So you're saying about this formal model in Coq and this tool Sigma. Can you tell more about it?
Yeah. The formal model is kind of a restricted version. We did a translation from a while language. You have a simple imperative language. You have while loops, assignments, and we kind of translate them back into lambda calculus or a functional program. And the translation is basically proving the translation, or the Coq stuff is proving the translation preserved semantics also aside. And this is a bigger context here is we're doing this translation or lifting from lower level imperative code to functional code or functional representation to allow more verification. And in this way, we have a collective form or representation for values that are like arrays or linked list. They are represented by a form that is indexed by the loop iteration and also indexed by the programming context. That's all in the functional representation of the program. And on that representation, we can easier do a bit more verification, especially those involving loops. That's actually is a project I did in my first semester at Purdue.
Oh, really?
Yeah, that's
forever
the first one. Yeah, it's like forever. It's eventually also finally get published almost 2 years later.
I wish I was that patient. Good.
Well, you will get there. Yeah, eventually those good work will publish anyway.
Yeah. I think that gives hope for sure. And then there is here talking about the smart contracts and how those ideas of defending against attacks is important, because at some point there was a bug of $8.1 million because of a smart contract bug. That is insane.
Yeah, those are real bugs already happened. We just see if our approach by tweaking those things can easier to prevent those bugs. But those numbers to some degree they're real, but it's not something. Well, it's something we use to validate the effectiveness of our approach. Those people in smart contract crazy. A lot of money going into this year, and also a lot of money has been stolen from those projects.
Oh yeah. I don't know. I think it's exciting. I don't know, having distributed ways to store money. I think it's a worthy endeavor. It's tough a little bit because security is a very complicated issue, but
yeah, for smart contract, I don't know. People always have kind of opinions on both extreme. One side is really just a future of, I don't know, computing or financial applications. The other side is probably just it's all fraud. It's all.
Yep. I've been in Twitter for too long, and I've seen how crazy those things. Yeah. But come on, we don't need to go to any of those extremes. As I was saying, I think it's an interesting, worthy endeavor in the sense of it's distributed system for sharing money in an interesting way. Period. Worth endeavor.
I'm not so sure about the market here, but I guess this underlying idea about blockchain, about distributing those ledgers, that could survive, or in the future we will see different forms there. So it would be still interesting and meaningful to look at those things.
Yeah, if you look at the original Bitcoin paper, where like he's solving a hard problem that was open in computer science. Like how to store something that is immutable, right? and how to do the transaction in a way that is safe in this storage unit. Yeah, blockchain is a very interesting piece of idea in that sense.
Yeah, especially now it's kind of marketed as Web3.
I don't even know what that is. Yeah, like they're saying what, like, that is the future of internet.
Yeah, like Web3, right? It's kind of those blockchain are really like a giant web, and people have a wallet or whatever the way to interact with the blockchain, right? There are also efforts on building storage or content platform on those blockchain stuff, right? Thinking about a more distributed way about building websites that each user can contribute something or can own some content on the blockchain. It's not only about financial applications, but also more about the general way that users produce content and consume content and own those content.
Interesting. I don't want to sound, like that I'm diminishing, but this really reminds me of wiki formats, which is, like how to distributely build a website and knowledge. It's just a wiki, no?
But the wiki still has a central server, right? For
I see.
Web3, it
Gotcha.
doesn't.
Gotcha.
That's kind of the selling pitch here, I guess. Yeah, it's interesting. Yeah.
I hate when someone does that to me. Like you get excited explaining an idea, and someone is just like in the middle of your presentation. But isn't that just this? You're like, no, you're missing the whole
point. Well, as people, we can only understand those things from the point of view of what we already understood.
Exactly. Yeah, it's tough. These ideas of sharing knowledge and giving ideas, and also I don't know. I think there is something about human nature where we're kind of defensive with what we already know, and we're kind of defensive, like I don't want to know more in a way. So you come up with this amazing idea, like people we are usually we avoid. Right? No. That's I don't have that problem here.
That's great. You have an open mind. Yeah.
Well, I mean, yes, I have to. I'm here to learn with my guests and all of that. And moving forward, then talking about learning, you've done so much work that I'm blown away. Like it's too much stuff, everything. And in the end here of your statement, you still have stuff about compiler for quantum computing. How is that going?
Well, I'm still learning those stuff.
Okay, good.
Yeah. Right. Yeah, so there's some stuff. I mean, it's always a cool word to add quantum to everything, right? We know. I mean, I have seen this many years ago, but I guess for a long while I don't really understand anything about quantum. But the thing is, I think I went to some conferences. That's maybe USLA Boston 2018. There's a tutorial or something about quantum programming languages, or kind of like what PL people can do for quantum computing. I stayed there for a while. I see, oh, that's cool that people in my area are also looking at this problem. Maybe I should pay a bit more attention later. I think the real thing but I did several times to look at those things, but I gave up quickly. It's just starting with linear algebra, starting with those matrix stuff. I just get lost quickly. Yeah. Right. Especially you don't really see the connection with programming.
Yeah.
Look at those things. For me, it's pretty hard. I think the way that I can finally appreciate those things is, I think that's last year.
When Robert Rand, and he gave a talk about it.
Even before that.
That was a good talk. I could understand what was going on.
Yeah, even before that, I think that's a scheme workshop at I can't remember, it's 2022 or 2023. There's a paper about quantum continuation. It's kind of using continuation to define an interpreter for quantum programs. That's by Vikram and Amar Sabri, who's a professor from Indiana University. They kind of give a very functional Perl style program, like just I think 30 lines of code to write a scheme program. And this is a program that takes quantum circuit program as input and produce a result. It's really like interpreter, produce a result of all the possibility of the result. This is kind of the nature of quantum programs, right? You have the distribution about each possible result. And this is a way that I can finally look at this program to see, oh, this is scheme code that's using continuation, and those stuff I can make sense. And to see, okay, this kind of give a dynamic semantics for quantum circuit program, where I can finally make sense at the operational level. That's a way I started looking at those things seriously. I mean, it's a really nice paper. It's just, I think, 12 or 15 pages. It's very accessible if you already know some functional programming. Highly recommended that.
So what's the high level idea here? What is the complications for building a compiler for quantum computing? I mean, I know for a fact that this must be hard and we have to be careful on how to build things, but give us a high level introduction of what is going on in this field.
I think it really depends on what we mean by compiler here. So on one side, people have already developed the hardware or prototypes of the hardwares for quantum computing, like IBM or D-Wave or IonQ. Those startup companies and big companies, right? They're building real hardware to perform computations, right? There are different ways to build those quantum computers. Semiconductors, some fancy trapped ion stuff I don't really understand. But that's a hardware. It's kind of like the ISA for compiler people, instruction set architecture, right? And that's kind of the problem. If you really care about running quantum programs on real hardware, then you need to compile your programs to those underlying hardware. That's one side. The other side, it's perhaps more interesting to me, is what is the semantics for those quantum programs, and how can we developing interpreters or relating those different styles of interpreters and compilers at a logical level or operational level without touching those hardware. That's also a way that I think that most of the work in the PL community is doing. Right, you can do optimizations for quantum programs, verification of quantum programs. I mean, anything traditionally you have done for classical computation, you can also do it for, different way, perhaps, for quantum computing. I think for me, I see this is a connection where those my work on reachability types and compilers can be also applied to quantum computing, especially in the sense that those reachability types, they can track aliasing, right? And, or reachability of different resources. And there's a similar correspondence in quantum computing, which is called entanglement. You can think of those qubits. Those qubits, they are primitive notions of resources in quantum computing. And each qubit, it represents kind of a distribution about value. And two qubits, they can be related or associated. And that is called entanglement. In the sense that if you change the distribution of one qubit, the other one is also changed accordingly, following the underlying quantum mechanics. And this is those qubits are related, and you can track those relations or associations of qubits as reachability in a static fashion, given by the type system, right? And you can also track separation, that is kind of the absence of reachability in a similar way. That's where I see my work has the potential to be applied to quantum computing. And also, if you think about side effects, in traditional programming or classical programming, you have, say, memory deallocation, right? You have a pointer, you just free this pointer, right? That's a side effect. It also distracts the underlying resource and also affected all aliased pointers. And in quantum computing, there's a similar thing called measurement. And it's an irreversible operation applied to a qubit to collapse those uncertainty values to a certain logical bit. And also this measurement process is not reversible. it's kind of like memory deallocation. And once you apply measurement to one qubit, all other entangled qubits are also deallocated. So this is where I see some of the similarity between classical computing and quantum computing, where I felt like my work on reachability types can be applied to there, especially to design a new language, given those capability to track entanglement, separation, side effects there.
Yeah. I can definitely see that, especially these ideas of the measurement, or just collapsing kind of memory deallocation. It's very interesting, very very cool stuff. But yeah, quantum computing ideas it's really goes above my head, as you were saying initially. Too much linear algebra, and it's very interesting too how I don't know about quantum computing necessarily, but like I started trying to understand this a little bit, at least like some basic understanding of what is quantum mechanics. And very very fast it comes to a point where our intuition of what the real world should be just doesn't make sense anymore, quantum speaking, and you just have to trust the mathematics, right?
Yeah.
Just have to, like, no, the mathematics is saying this is going to happen, so we don't care, right? um I feel there is definitely some analogy here between this quantum world where things just make sense mathematically and that's it, and doesn't necessarily, I'm not going to necessarily understand or see what's going on with the ideas after Gödel's incompleteness theorem, where you just trust that some things are not going to be solved, and that's it. Like, yeah, that's it.
Yeah, that's a trouble I have too. I don't really understand too much about the quantum mechanics. I think so far my understanding works at the operational level for quantum programs, those quantum circuit programs where you have gates, you have wires connecting those gates. And for each gate, it has a sort of semantics, using the terminology we are familiar with, right? That's the way I can make sense about those things, what it does to treating it as a program, right? And also, I think continuation is a good way to look at it, especially in those quantum physics. There are different interpretations. One interpretation about those quantum phenomena is parallel worlds. And if you think about those correspondence in continuation, you just have the continuation, you can have multiple continuations that corresponds to the parallel worlds. At a certain point after this point, you have two possibilities, and that corresponds to two different continuations to be executed.
Right.
That's a very beautiful correspondence I see from the scheme workshop I mentioned earlier.
Interesting. Very interesting. Huh. I'm a little rusty with the continuation passing style stuff, but I remember something along the lines of, at some point you can have multiple continuations, and it's kind of like you don't know which one is going to be chosen, right? Like both are going to be chosen, or none are going to be chosen.
Yeah, that's the way to go. Yeah,
that's very interesting. I was gonna say something more about the. Oh yeah, so I don't know. It's something that I have in my mind, and I think that the answer is negative. But I don't know if you looked into this. But are quantum computers, like, they don't add computational power to Turing machines, right?
I think the answer is no, but I'm not expert there.
Yeah.
From what I read, it's no.
Yeah.
And what can be effectively solved by quantum computation is a computation class called BQP, if I remember correctly. It's kind of basically like a P time thing for quantum computing.
Is there where RSA is in, like regular cryptography is part of that computation class? Is that the idea?
You're talking about the integer factoring. That's the underlying algorithm for RSA, I think. Yeah, I think that's one example you can solve in polynomial time
I see.
on quantum computer. I think that's the first convincing example about the practical use about quantum computation. Where traditionally it's exponential. I'm not sure.
But it's faster.
Yeah.
That's the important part.
It's faster.
I didn't know about this thing that you just mentioned, that there is a computation class. Is that how is it called? That it's a
BQP.
Yeah.
That's bounded error quantum polynomial time.
Yeah. That makes a lot of sense. And why people are kind of little worried about quantum computing and trying to find algorithms that are quantum resilient.
Yeah, especially for those cryptography stuff.
Mm-hmm. Yeah, I remember saying this a couple of years ago, that a lot of those the important applications like credit cards and stuff, they're already moving towards quantum resilient computation, which is very nice. I think that's a major part of cryptography research. I might be now. We are both outside of our expertise, but
I don't know much about that.
Maybe this is a good opportunity for us to move on, because
sure.
Both of us just making guesses here. Well, I think we covered pretty much everything that you've worked on. That was a lot. It's very, very amazing, very interesting. You've done a lot of work. How's the application process going on for your professorship? Can you tell us more about how the application process works? I'm curious.
Yeah. So the journal is, I think, from last roughly September time, I started working on my application. And for a faculty job, you need to prepare your CV, prepare your research statement, a teaching statement, and also some diversity statement. Some places doesn't require the diversity statement, but I need to prepare that anyway. And you also need people write letters for you, from 3 people to 5 people. And it takes a while to polish those research statements. I think timeline-wise, I get submitted my application, most of them in late November, and some of them in early February as well. And then you get a number of phone interviews, and some of them, you pass the phone interviews, then you will be invited for on-site interview to visit the university and department.
Who performs the phone interview?
What?
Is it the department head? Who is in charge of doing the phone interview?
Usually there will be a search committee. Search committee is a number of people, and there's a search committee chair. The chair usually will be in charge of the phone interviews.
Are they in the field, the department, or just
not necessarily in the field? Mm-hmm. Not necessarily in the field. They could be someone else, but they look at the application and they may consult opinions from other faculties in your field to see whether it's good. And sometimes department chair is also involved. I got emails from those department chairs for phone interviews as well. So it's common, but generally there is a search committee that work with department chair as well. So you get phone interviews. Usually it's 20 minutes to 30 minutes. There's roughly a standard set of questions to ask about what is your research, what's your next plan, what's your funding plan, how is your teaching style, how you mentor students, those kind of questions.
How long is it, the interview?
It's usually 20 minutes to 30 minutes.
How can you explain all that in 20 minutes? You need like 1 hour. Come on.
Well, it's not supposed to be taking 1 hour for all the people, right?
Okay, yeah.
Some of the department they can interview 50 or 80 candidates. It's just not possible.
No, let's
gather all people.
Let's pause for 1 second and look at one of those questions that you just gave. So, what is your plan for getting grants? You can talk about that for 20 minutes, right? Come on.
Sure. You can talk about it in 20 minutes, but I think the tricky part is how can you convince other people in 2 minutes.
What was your approach? Did you approach that issue?
That's usually highly related to my research future work, right? And you could also talk about you are aware of those funding agencies and what they're
I
looking
see.
for,
Gotcha,
right?
gotcha.
NSF programs, and also show that you have experience involved in those proposal preparation, proposal writing, so you know roughly the process and what's how it works, at least in the United States.
Mm-hmm. What are the big agencies here in the U.S.? Is it NSF, NASA? What else?
I think the major ones in NSF, there are NASA and DARPA,
DARPA,
DOD, Department of Defense, and Department of Energy.
Energy,
and also Energy also has programs. They support some high performance computing or compiler work as well. I know. There are also, I think, NSA for security stuff or crypto stuff, right?
Right.
Those are mostly government funding agencies.
All right, so everyone who's listening, you just take notes on all of those terms. You've got one of the questions done.
Yeah. Right. Where were we?
Right. So we were talking
interviews.
Yeah, there was a phone interview and then the on-site.
Yeah. Then they invite you for an on-site visit. Some of them they are virtual. Some they have to be virtual because, like, for Canada or other places I can't go, then it has to be virtual. But most of them will be physical.
Do they pay for everything, or you have to take?
Yeah, they will pay everything.
Nice.
They will pay the tickets, the hotel.
How long does it usually take? Is it 1 or 2 nights to stay there?
Usually we'll be staying 2 nights.
2 nights.
I think the typical schedule is a full day's interview from night or from 8 or 9 a.m. to 4 or 5 p.m.
Gotcha. So you sleep again and you leave the next day.
Yeah, you arrive the day before and leave the day after.
Yeah, gotcha.
Sometimes you'll schedule for 1.5 days. For the second morning, you'll also have some meetings to talking with faculty members or students. So that's also typical. So it's a kind of, for each individual visit, it takes 3 days. And traveling can be exhausting.
Yeah, that sounds very exhausting. To spend a couple of months traveling the country. Sounds fun too. You get to meet a lot of places and a lot of people.
Yeah, that's a fun part. I'm trying to enjoy it.
It must be very exhausting.
Yeah. So, and those interviews, you also need to give a job talk. And I'm sure you know at Purdue they also.
Oh, so many job talks this semester.
Yeah, so many job talks.
It's exhausting.
Yeah, like every day in the morning I see the email. There's
every
some
single
job
day.
Email.
And it's funny because the department they're really like, hey guys, you have to come to the job talk because it looks really bad in the department. There's nobody there, right? So they're gonna bring like coffee and pizza and try to gather students to show up. It's funny.
Yeah,
it's good for us too.
Right, especially I think Purdue is going to hire a lot of people this year.
Yeah, that's what I'm seeing too. But well, I think Purdue grew a lot post-COVID.
A lot, yeah.
The university is just so crowded. It's so extremely crowded. Definitely need more professors.
Yeah, I think when I joined Purdue as a first-year PhD student, there are around maybe 50 faculty members. I think now it's 80 or almost 90. I don't know the exact number now, but it really grows a lot. Yeah,
it's insane. To be completely honest, I feel a little worried about this boom in the higher education. I feel like it's growing too fast without without a higher plan of what is actually going on. Especially because universities here in the US, they're very interested in the money of these students, so they're just like, let's grow. And I don't see necessarily that being converted in this care about the education itself, and that's I feel a little scared about that.
Right. I think those growth, they are mostly kind of reflected by the enrollment in undergrads, especially at Purdue as a large public school. The enrollment of undergrads computer science or related majors, they are also seeing a big wave now. but it can't be just growing all the time, right? At some point later, maybe the market we hit the winter, right? Then those students will hard to find a job, and no one or less students will choose a computer science major. That's when the problem comes later.
So you're saying that things are gonna be even worse later, because if the department has to like, if it grew too much, then it had to shrink afterwards, and so maybe some professors have to go.
Or the hiring will be much less, and more professors will retire, then the whole size of department will shrink again, right? I think that's a thing we have seen in the past 20 years. There are waves like that.
Yeah, that's a way to look at it.
Right.
Sure.
If some of the departments, they have more senior people, they retired, and the university decided there's no more headcount for computer science, they're not hiring anymore, then the departments will look like not too many new people or assistant professor joining there.
Yeah, there are cycles.
There are cycles, exactly.
Especially right now with the rise of LLVMs, CS is just so extremely hyped right now. Everyone wants a CS job as a developer, and right now is very crazy. I think like when you and me, when we started studying computer science, was people are not paying this much attention, but now this is just insane.
Yeah, I think at the time those deep learning already get a lot of more attention, those images stuff, but not comparable to the hype now we have experienced. Yeah.
How do you feel about, okay, so you're going to these universities and you're doing these job talks. I would expect that they're trying to, like the biggest part of our department is ML. It always is ML, AI and ML. So how do you feel that there, like the space for a PL researcher? Do you feel like it's okay, it's still normal, they're still looking for PL, or when you get there with your research, maybe you feel that some of the professors are going to be a little more protective, that they actually want more ML people? How do you perceive this?
From my experience, I think most of the time, if you're doing PR work, not in a intersection of PR and ML, you don't really have much or concern or interaction with people working in ML, because there are very little shared interest, unless you want to say, for example, program synthesis or neurosymbolic stuff that's getting into machine learning or AI, right? Or maybe for compilers for AI, that's also a legit system-ish area. But I don't feel like people are getting protective for those things. But at the end of the day, it also depends on very much about department culture, what's the focus on of the hiring. A lot of departments, at least from what I have seen in this cycle, most of the departments are definitely interested in hiring AI people, right? And also large people working in large language models as well. But I think it's fair to say, if I get an interview, it's a sign that the departments want to look for people working PR or compiler, which is already a good sign for me. It's kind of like a bias for me, because for those departments, they don't want PR people, they won't interview me at all. Yeah.
Yeah, it reminds a little bit of what there was a junior professor that visited our department last year, and he was saying how he got the perfect position in Portland, exactly because they needed someone to teach the PL course.
Right. That's also highly depends on the teaching need, right? It's always a need to teach. Well, I think at least this moment, I think we can still say this, to teach, say, for compilers, right? Especially for undergrads, teaching the general notion or foundations of programming languages. That's kind of all required for education of undergrads. There's always a need for this. It's just some of the university there or departments they're more teaching driven. That they really need someone to teach this class. Some of the larger departments they're more liberal, I guess. They already have enough people, but they can also looking for people to strengthen their direction in PL as well.
Well, but so you visit the university and then you go through some interviews in person. What's next?
You wait.
You wait and you hope for the offer.
Yeah, but it's kind of a process, I guess. It's a dynamic process. You will have a bit more interviews, and then you may have multiple offers, and you can see which is one that fits the best, or you can negotiate some of the term. I'm not there yet, but hopefully I will.
No, yeah. You definitely will. You definitely will. Really good CV. Oh, I think this then covers everything that we wanted to cover. Is there anything else that we didn't talk that you would like to mention, or?
I think that's most of all. I'm not sure if you want to talk more about academia, environment. I'm not sure to what degree, or you want to talk about that.
Well, it's up to you, to be completely honest. Do you think there is anything in particular that you would like to address when you become a professor? For example, I personally, I feel troubled about the publication process and how complicated, how weird things are with the publication, and how little time professor have, like, to do surveys. And I firmly believe that we have to rethink most of our publication process and how things are going down from there, because things are weird and too many PhD students, and we cannot wait, like, that sort of ideas. What are your concerns, or if you have any?
Yeah, I think publication process is a issue there. It's get a lot of randomness factors during this publication process. Especially, it can be very frustrating for students. I can totally relate to that. I think people are perhaps getting more, different ways to deal with publications. Some people, they go into more journal mode, right? Especially in our field, people submitting papers to JFP, Journal Functional Programming.
I wonder how much that can be a blow into your application, right? Because then your application is not going to have first tier publications, and you're not even getting interviews,
For top class and JFP, I think that's still considered very good, right?
Mm-hmm. I'm not sure. I don't know what are the criteria, the field criteria.
Yeah, that's definitely possible as well. I felt like I heard really a lot of good feedback from people who have submitted to top class. It's very more thorough review, more reasonable reviewers, and reasonable expectations, and no page limitations. So you can, I guess, to have less constraint and also have an opportunity to address those concerns thoroughly. But I'm not sure about the scalability, right? About journals, especially you look at those journal publications, very little compared with conferences. But for this field in PL, I felt like we're not like machine learning. There are thousands of papers or 10,000 submissions.
Yeah. Oh god. Yeah, I have some ML people, some ML friends, and like they can work in a project for 6 months and have a solid submission, which is absolutely inconceivable for our field. We need to work 1 year or even 2 years to get
at least
a reasonable submission. So
yeah, that's true. Yeah, but there are also I don't know. I felt like there are newer efforts on changing the publication mode. I see some changes in eCoop. Right, eCoop, they changed to like at the submission time, there's no page limitation. So less hassle when you prepare the first submission. You don't have to really shrink the pages to fit into, say, 20 pages, 25 pages, right? And also, those 2 rounds modes is mostly adopted by Uppsala and eCoop now. So you have more opportunities to submit, and you have revisions. It's more like a journal thing. Like one of our paper at Uppsala, it's got 2 rounds of resubmission or revision. We submit to one round of Uppsala, get some feedback, and resubmit to the next round after 6 months. And in the second round, we still get some feedback or comments or revision, suggestion, or requirements. And then after 6 months, we resubmit again to Uppsala. And this is guaranteed, or at least from the time we experienced, those 3 rounds, we have the same set of reviewers for the same paper.
Yeah, that's important. That's really important.
That's really good. Especially for, otherwise, if we resubmit to some other venues, you get a different set of reviewers, you get different opinions.
Different biases.
That's just that's totally get more randomness into this process. So I think my experience is getting a bit better, but people need to be more careful about the strategy about submission sometimes. I mean, it's a game. Sometimes we need to have a strategy to deal with it. Yeah. But the other issue, I think, at least from what I have felt, I mean, I have not become a professor there, but what I have felt is professors really put a lot of time into writing proposals. And those are major efforts, and also part of the what is called the tenure evaluation criteria, one of the criteria there. And some other places, unlike US, they don't need to put a lot of efforts there. I talk with people in Canada and Singapore. They have more, well, I shouldn't say easy, but yes, it's easier to get funds compared with US system.
Yeah. Mm-hmm. It's more guaranteed, let's put it that way.
Yeah, or you have higher chances. You have less competitions, maybe. Yeah, that's kind of more support from the university, or more support from the government funding agency, or less competition in some degree. That's true as well. In that case, the professor have more time to work on the actual research instead of worrying about, do I have enough money to support my students, right? Do I have enough money to pass through the tenure process, right? And but the United system states it's right. NSF, it's a big factor there. There are other funding agencies, and the university had overheads from those fundings.
Oh yeah, sometimes I think Purdue takes like 40% overhead. It's insane.
Yeah, I don't know the exact number. Usually at least 30 to 40, I think. Yeah, that's basically kind of. I'm not sure it's really fair to say, like, professors are making money to the university.
Yeah,
to some degree, and that's kind of the way you show that you can support your group, you can make a sustainable group of students and support your research as well. That's the evidence. That's part of the criteria to be promoted, right? And different systems work in very different ways. But I would say if there are better ways to allow faculties to focus more on the research, that would be better. But this is not something I can change, right?
Exactly. That's the thing that we're kind of, especially in this highly departmental setting, like, it's not up to us. It's a highly, how can we say? It's already how the system is set, right? It would be similar to saying, oh, the US is the only country that gives tips. Let's abolish tips. It's not something that is possible to be done from one day to the other, because like it's already how the whole culture works around tipping, right? And all of these issues that we're talking about is like it's foundational to how the whole university works right now and how it's able to sustain itself. So
exactly.
It's very complicated. It's very complicated. But that's why I'm curious. That's why I'm going to Europe next year. I'm gonna spend some time hanging out over there, and I wanna see, like how are the departments working over there, because it's definitely different, but I'm not sure how much. So
Yeah, I'm sure that would be a good experience. Yeah, especially you have been visited those countries, you can see how different department works and
what is the culture? Like in order to see the
exactly.
culture, you really need to be inside over there. And maybe I don't know, maybe I'll have new ideas to be vocal and annoy people with this podcast.
Yeah, of course.
Guannan, it was so good to talk to you. It was a really nice Saturday afternoon for us.
Yeah.
Any final thoughts, closing remarks?
Not too much. Yeah, I guess. It's really happy to talk with you, and thank you for inviting me to your podcast.
Yeah, for sure. It was great. You're still on Twitter?
What?
Are you still on Twitter? X? Now these days?
Yeah, I'm still on Twitter.
All right, I'll make sure that you guys follow him on X, Twitter. I don't know if you post there too much, but I'll leave your handle in the description of this episode.
Yeah, thanks for that.
Yeah, so
all right.
Thank you so much for coming.
Mm-hmm. Yeah, thank you, Pedro.
Well, that's it for today's episode. Thank you so much for you guys to be here. I hope you enjoyed this episode as much as I did. Guannan is just so smart. I think he's probably the most prolific student in programming languages here. He's been with Tiark for a long time. Yeah, he's absolutely awesome, very extremely smart. It was really, really cool to have this conversation. So, well, that's it. I have to apologize that I took so long to post an episode this year. I swear it wasn't really my fault. I just couldn't find anyone that was available at the beginning of the year. Beginning of the years are usually kind of pretty hectic. But that means that I have a lot of work in March. I have 3 or even 4 interviews lined up. So good for you guys. And it's gonna be a hectic month for me. Let's do this. If you are here, don't forget to enter our Discord. Go to our Discord and become a part of our community. Don't forget to donate a little bit, give us some support on Ko-Fi. Go to our website, type34.com, send us email. You know the stuff. And don't forget the stuff that I said at the beginning. We are currently looking for partners. Very important. What else? That's it? Well, see you guys next time. Enjoy yourselves.